Welcome back to the deep dive. Last time, we navigated the blueprints of IoT with our discussion on architecture and design principles. Today, we're taking a thrilling leap from the theoretical to the intensely practical, really getting into the hardware.
Good morning, everyone. Thank you for joining us today. Yeah, I'm truly excited to unpack the tangible heart of the Internet of Things. We're talking about the foundational physical components. The digital nervous system of IoT, the sensors that perceive, the actuators that act, and the microcontrollers that are the brains bringing these systems to life. And this is really crucial stuff. For innovators, particularly in regions like Canada with its strong environmental monitoring, resource extraction, and, advanced agriculture sectors, understanding this hardware isn't just about curiosity, it's really about driving real-world impact and global competitiveness.
That's a fantastic setup. So our mission today is to truly understand these crucial components, the nuts and bolts, so to speak.
Yeah. Exactly. And to guide us through that, I thought we could structure this as a Q&A session. I'll lay out the key questions we need to tackle up front, and then we can dive into each one.
Sounds like a plan.
Yeah.
A roadmap.
Precisely. So here are the questions we'll be covering today, in this order. 1. What are sensors, and could you give a few examples of the most common types used in IoT? 2. You mentioned sensors for detecting gases in proximity. What are some applications for those? 3. If sensors are the senses, what are actuators? 4. What are some of the different types of motors that are commonly used as actuators in IoT and robotics? 5. What about controlling high-voltage devices? How can a low-power microcontroller safely switch a home appliance on or off? 6. Now for the brains of the operation. What is a microcontroller? 7. Let's talk about specific platforms. Why is the Arduino so important in the world of IoT? 8. What about the ESP32? Why has it become such a powerhouse for connected devices? 9. How is a Raspberry Pi fundamentally different from an Arduino or an ESP32? 10. To interface with these microcontrollers, we need to understand signal. What is the basic difference between an analog and a digital signal? 11. How do microcontrollers bridge this gap between the analog world and their digital nature? 12. What are GPIO pins, and what role do they play in connecting hardware? 13. For more complex devices, what are communication protocols? And can you give an example? And finally, 14. To conclude our discussion on hardware, what is the key takeaway about the importance of these physical components to the Internet of Things?
Wow, that's a comprehensive list. Covers everything from the tiny sensors to the communication methods.
That's the goal, a solid foundation in IoT hardware. So shall we dive into the first question?
Absolutely. Let's start with the basics. If we're building this digital nervous system, where do we start? With its senses, right?
Exactly. So question 1. Let's start with the senses of the machine. What are sensors, and could you give a few examples of the most common types used in IoT?
Okay.
Well, sensors are essentially the vanguard of the IoT ecosystem. They're the devices that translate physical stimuli from our world, light, temperature, motion, maybe even specific gases, into electrical signals, signals that a microcontroller can actually interpret.
So they're the translators between the physical and digital worlds.
Precisely. And the real power often comes not just from one sensor, but from combining data from multiple types. We call this sensor fusion. Imagine combining temperature and humidity data to predict, say, condensation risk, or maybe using motion and light data together to make energy use in a building much smarter. This fusion unlocks predictive capabilities that, a single sensor just can't provide on its own.
Interesting. So it's about the bigger picture painted by multiple senses.
Exactly. Now, as for common types, temperature sensors are, they're everywhere. Think smart home thermostats, controlling your HVAC, monitoring industrial processes, or even ensuring the integrity of the cold chain for food and pharmaceuticals. You often see components like thermocouples, RTDs, or simple integrated circuit sensors like the DHT11 or DHT22, which handily combine temperature and humidity sensing.
Right. I've seen those DHT sensors in hobby projects.
Very common. Then you have motion sensors. These detect physical movement. The most common type is probably PIR, passive infrared, which detects changes in infrared radiation, basically body heat. They're fundamental for security alarms, automatic lighting systems, and lots of energy-saving applications.
Makes sense.
And of course, GPS modules. Technically, they're receivers listening for satellite signals, but they function as powerful location sensors. They give you precise coordinates, latitude, longitude, absolutely vital for asset tracking, managing vehicle fleets, navigation systems, and setting up geofences.
So those cover temperature, movement, location, the basics of environmental awareness.
They do. Which leads nicely into our second question. You mentioned sensors for detecting gases in proximity.
Yeah.
What are some applications for those?
Yeah, those sound a bit more specialized.
They are, and often critical. Gas sensors, for instance, are designed to detect the presence or concentration of specific gases. Their most obvious role is life-saving, think carbon monoxide detectors in your home or smoke detectors. But in industry, they're indispensable. Monitoring for flammable gas leaks like methane in processing plants or tracking air quality by measuring pollutants like NOx or VOCs. This is crucial for worker safety and environmental compliance.
So safety and regulation are big drivers there.
Definitely. Then you've got proximity and level sensors. These detect objects nearby without actually touching them. Ultrasonic sensors are a great example. They emit sound pulses and measure the time it takes for the echo to return. You find them in vehicle parking assist systems, helping robots avoid obstacles, and even for measuring the liquid level inside large industrial tanks, giving real-time inventory data.
Like sonar, basically.
Very much like sonar, yeah. Infrared or IR sensors work similarly, but use infrared light instead of sound. And we can't forget humidity sensors. They measure water vapor content in the air. Essential for HVAC systems, weather stations, but also in specialized agriculture like greenhouses, or even preserving food and delicate artifacts in museums.
Right, controlling the environment precisely.
Exactly. And finally, light sensors, often called photoresistors or LDRs, light-dependent resistors. Their electrical resistance changes based on how much light hits them. Simple, but effective. They automate streetlights, adjust your smartphone's screen brightness, and are even used in agricultural IoT to monitor how much light crops are getting.
It's amazing how many ways we've found to digitally sense the world around us. Okay, so sensors give devices awareness.
That's right.
But awareness isn't enough, is it? The device needs to do something with that information, which brings us to actuators, right?
Precisely.
Yeah.
Question 3. If sensors are the senses, what are actuators?
Yeah, what are they?
Simply put, actuators are the muscles of the machine. They're the components that take an electrical signal, a command from the microcontroller, and convert it into some kind of physical action. They're what actually close the loop in an IoT system. They allow the system to not just observe or monitor the world, but to actively influence it, to, open a valve, turn on a light, spin a motor, make something happen.
Okay, so sense, think, act. Actuators are the act part.
You got it.
And you mentioned motors. They seem like a really common way to create action. So question 4, what are some of the different types of motors that are commonly used as actuators in IoT and robotics?
Right. Motors are absolutely central, converting electrical energy into physical motion, countless applications. We generally encounter 3 main types in IoT and robotics. First, you have DC motors. These are, the simplest kind, typically 2 wires. Apply voltage, they spin. You control the speed mainly by varying the voltage level. You find them everywhere, fans, toys, simple wheeled robots. Very cost-effective for basic continuous motion.
Okay, simple and direct.
Then things get more precise with stepper motors. These are fascinating. They don't just spin continuously. They move in very precise, discrete steps, like tick, tick, tick. This gives you incredibly accurate control over the position and the amount of rotation. That's why they're indispensable in things like 3D printers, CNC machines, and many robotic systems where exact positioning is absolutely critical. They trade that smooth speed for pinpoint accuracy.
So that's how 3D printers get so precise.
Exactly. And the third type is the servo motor. Now, a servo isn't just a motor. It's usually a packaged unit. It contains a DC motor, some gears to increase torque, and importantly, a control circuit. You don't just tell it to spin, you command it to go to a specific angle and hold that angle. This makes them the absolute mainstay for things like joints and hobbyist robot arms, many industrial automation tasks, and control surfaces in RC vehicles. Anywhere you need controlled angular movement.
So DC for spinning, stepper for steps, servo for angles. Got it.
That's a good summary. Each tool for the right job.
Okay, that covers motion pretty well. But what about just switching things on and off? Especially big things like a lamp or a washing machine. That seems like a common IoT task. How can our tiny, low-power microcontroller safely control a high-voltage appliance?
Excellent question. That leads us to question 5. What about controlling high-voltage devices? How can a low-power microcontroller safely switch a home appliance on or off?
Yeah, you don't want 5 volts meeting 240 volts directly.
Absolutely not. For that critical task, the key component is the relay. Think of a relay as an electrically operated switch. It uses a very small, safe electrical signal from your microcontroller, maybe just 3.3 or 5 volts, to control a completely separate, much larger electrical circuit. This provides electrical isolation. It's absolutely crucial for safety. It lets your little microcontroller switch mains, voltage appliances, industrial motors, big lighting systems, whatever it might be, without any direct electrical connection to those dangerous high voltages or currents. It's the essential bridge and protector.
So the relay takes the gentle tap from the microcontroller and uses it to throw the big power switch.
That's a great way to put it, yes. And while we're talking actuators, we shouldn't forget simpler ones. LEDs, late-emitting diodes, are very common actuators, even if they just produce light. They're used constantly as visual indicators showing if a device is connected to Wi-Fi, if it's operating normally, or maybe flashing to signal an error. Simple but effective communication.
Right, status lights.
Exactly. And for sound, you have speakers and buzzers. Buzzers provide simple auditory feedback, beeps, alarms, confirmation tones. Speakers can, of course, reproduce more complex sounds, like recorded messages or even enabling voice interfaces.
So actuators cover a wide range, from heavy lifting with relays to simple feedback with LEDs and buzzers.
They do. They provide the physical output.
Okay, we've got senses and muscles, actuators, but neither works without coordination. That brings us to the core, right? The brains.
Indeed. Question 6. Now for the brains of the operation. What is a microcontroller?
The heart of the device.
You could say the heart or the brain, yes. The microcontroller unit, or MCU, is essentially a compact, integrated computer on a single chip. It's amazing what they pack in there. You've got a processor core to actually run the code. You've got memory, both RAM for temporary data while it's running, and usually flash memory to store the program code itself. And crucially, it has built-in input-output peripherals to talk to the outside world. Its fundamental job is to execute the software instructions, read the data coming in from sensors, process that information according to the program, and then send commands out to the actuators. It's the dedicated intelligence for that specific IoT device.
A tiny, dedicated computer running one specific job.
Pretty much, yeah. Optimized for control tasks rather than general-purpose computing.
Okay, and when people start with IoT, especially hobbyists, one name always comes up. Which leads to question 7. Let's talk about specific platforms. Why is the Arduino so important in the world of IoT?
Arduino. Yes, it's arguably the most important ecosystem for getting started, for hobbyists, education, and even rapid prototyping in professional settings. Why? Primarily, its simplicity and its open-source philosophy. An Arduino board, like the classic Arduino Uno, takes a microcontroller often from the Atmel AVR family and packages it with all the necessary support circuitry to make it easy to use. Power regulation, USB connection, easily accessible pins. But the real strength is the ecosystem. The Arduino IDE, Integrated Development Environment, uses a simplified version of C++D, making the programming much more approachable. And there's a vast library of pre-written code for almost any sensor or actuator you could imagine. This means you can get a project, blinking an LED, reading a sensor, or controlling a motor incredibly quickly, often without needing to understand the deep, low-level hardware details.
So it lowered the barrier to entry significantly.
Massively. The main limitation, though, especially for standard boards like the Uno, is that they typically lack built-in network connectivity. You often need to add extra boards called shields to give them Wi-Fi or Ethernet capabilities.
Okay, great starting point, but maybe needs help connecting. So what if you need that connectivity built in, plus maybe more power? That seems to be where the ESP32 comes in. Question 8. What about the ESP32? Why has it become such a powerhouse for connected devices?
Right. The ESP32, from a company called Espressive Systems, has really taken the IoT world by storm. It's become a genuine powerhouse because it hits this sweet spot, an exceptional balance of performance, a ton of features, and remarkably low cost. It's a killer feature. It's a pretty powerful dual-core microcontroller that has integrated Wi-Fi and Bluetooth connectivity right there on the chip itself. No extra shields needed for basic wireless communication. This makes it a fantastic all-in-one solution for projects that need to be connected to the internet or other devices. It's significantly more powerful than a standard Arduino Uno, capable of handling more complex tasks.
And is it hard to program compared to Arduino?
That's the other brilliant part. You can program the ESP32 using the same Arduino IDE and many of the same libraries. So if you learned on an Arduino, moving to the ESP32 is a surprisingly easy upgrade path. This combination, the processing power, the built-in Wi-Fi and Bluetooth, the low cost, and the Arduino compatibility has made it an absolute favorite for both hobbyists and, increasingly, commercial IoT products, especially where wireless connectivity is key.
Powerful, connected, and still accessible. I can see why it's popular.
Definitely a game changer.
Now, this next one often causes confusion. People see another small board with pins, the Raspberry Pi, and think it's similar. So, question 9. How is a Raspberry Pi fundamentally different from an Arduino or an ESP32?
Ah, yes. This is a really crucial distinction to grasp. The Raspberry Pi is not a microcontroller. It's a single-board computer, or SBC.
Okay, computer, not controller. What's the practical difference?
The biggest difference is that a Raspberry Pi runs a full-fledged operating system, usually a version of Linux like Raspberry Pi OS. An Arduino, or ESP32, on the other hand, runs much simpler dedicated code directly on the hardware, what we often call bare metal, or using a real-time operating system, RTOS. Because it runs an OS, the Raspberry Pi is vastly more powerful. It has a much faster processor, more like what you'd find in a smartphone, dedicated graphics capabilities, much more RAM, and standard computer ports like USB, HDMI, Ethernet.
So it's literally a small computer.
Exactly. It does have GPIO pins, just like microcontrollers, so you can connect sensors and actuators directly to it. However, it's generally overkill for simple tasks and consumes significantly more power. Its real strength in IoT lies in more complex applications that need that extra processing power or the features of a full OS. Think of it acting as a central hub for your smart home, processing video streams from a security camera, running a web server, or maybe acting as a local IoT gateway that collects data from multiple simpler ESP32 or Arduino devices and then talks to the cloud.
So microcontrollers for dedicated device tasks, Raspberry Pi for more complex processing, coordination, or acting like a mini server.
That's a very good way to think about it. Horses for courses, the Pi is for heavy lifting, MCUs for dedicated control.
Okay, that clears things up nicely. So whether we're using an MCU or an SBC with GPIO, we need to connect things. And that involves signals. Question 10. To interface with these microcontrollers, we need to understand signals. What is the basic difference between an analog and a digital signal?
Right. This is absolutely fundamental. Microcontrollers and computers live in a digital world, ones and zeros. But the physical world we're trying to sense and control is, well, largely analog. An analog signal is continuous. It can represent an infinite number of values within a given range. Think of a dimmer switch. For a light, it smoothly varies the brightness. Or the voltage coming from a temperature sensor, which fluctuates smoothly as the temperature changes. Sound waves are another perfect example. Analog signals provide a rich, detailed representation of physical phenomena.
Smooth and continuous, like a ramp.
Exactly. In contrast, a digital signal is discrete. It only has a finite, usually very small set of distinct values. Most commonly in digital electronics, it's just two states. High GH, or low W, often represents 1 and 0, or specific voltage levels like, say, 3.3 volts for high GH and 0 volts for low. Think of a standard light switch. It's either fully on or fully off, no in between. This two-state system is the native language of microcontrollers and all digital computers.
On-off. Discrete steps, like stairs.
Perfect analogy. And bridging this gap between the analog ramp of the real world and the digital stairs of the microcontroller is a core challenge in IoT hardware design. The quality of that conversion matters too. For instance, how precisely you convert an analog sensor reading into a digital number, the resolution, can be critical in applications like medical devices or industrial control.
So the world speaks analog, controllers speak digital. How do they talk? Question 11. How do microcontrollers bridge this gap between the analog world and their digital nature?
They use specialized built-in circuits to act as translators. To listen to the analog world, they use an analog-to-digital converter, or ADC. An ADC takes that continuously varying analog input signal, like the voltage from our temperature sensor, and samples it, then quantizes it. It converts it into a discrete digital number that the microcontroller's processor can understand and work with. For example, a 10-bit ADC, which is pretty common, can represent the analog voltage range as one of 124 distinct digital values from 0 to 1023.
So it turns the ramp into a series of steps.
A very good way to put it. And for going the other way, when the microcontroller needs to speak analog back to the world, it uses a digital-to-analog converter, or a DSA. A die takes a digital number provided by the microcontroller and converts it back into a corresponding analog voltage or current. This might be used to, say, smoothly control the brightness of an LED, not just on and off, or to generate an audio waveform to be played through a speaker. These ADCs and DACs are the essential bridges enabling the digital brain to interact meaningfully with the analog environment.
Got it. Input via ADC, output via DAC. Now, how do these signals physically get into and out of the chip? You mentioned GPIO pins earlier. Question 12. What are GPIO pins and what role do they play in connecting hardware?
Right. GPIO stands for General Purpose Input-Output. These are the actual physical pins you see sticking out from the microcontroller chip or lined up along the edges of boards like an Arduino or Raspberry Pi. Their magic lies in their versatility, hence general purpose. Each GPIO pin can typically be configured in software to act as either an input or an output. When configured as an input, the pin listens to the voltage level connected to it. It can read whether a switch is pressed to take a signal from a motion sensor or receive data from another digital device. When configured as an output, the microcontroller can actively control the voltage level on that pin, setting it HIGH or LOW. This allows it to send signals out to control an actuator, like turning an LED on or off, sending a command pulse to a motor driver, or triggering a relay. They are the fundamental physical interface points, the direct lines connecting the microcontroller's digital core to the external hardware world.
So they're like configurable digital doorways for signals.
Exactly. Input or output, as needed by your program.
Okay, that works for simple on-off signals or reading basic sensor states. But what about more complex data, like getting detailed readings from a sophisticated sensor or talking to multiple devices efficiently? That sounds like it needs more than just high-all.
You're spot on. When devices need to exchange more structured information than just a simple digital state, we move beyond basic GPIO manipulation and rely on communication protocols. Which brings us to question 13. For more complex devices, what are communication protocols, and can you give an example?
Right, the rules of the road for data.
Precisely. Communication protocols are standardized sets of rules and procedures that define how data is formatted, transmitted, and received between two or more devices. They ensure everyone is speaking the same language. There are many, but let's touch on a few common ones used at the hardware level in IoT. A very simple one is UART, the Universal Asynchronous Receiver Transmitter. This is basic serial communication. It typically uses just two wires, one for transmitting data, TX, and one for receiving data, RX. It's asynchronous, meaning there's no separate clock signal shared between the devices. Timing is handled based on agreed-upon speeds, baud rates. It's usually point-to-point one device talking directly to another. Common uses include connecting a microcontroller to a computer for programming or debugging, or interfacing with modules like GPS receivers that stream data serially.
Simple. Two wires, point to point.
Okay. Then, a very popular and efficient protocol is iSoC, often pronounced I2C or I2C. It stands for Inter-Integrated Circuit. I2C is clever because it allows a single master device, usually your microcontroller, to communicate with multiple slave devices, like various sensors, memory chips, small displays, using just two shared wires, a data line called SDA and a clock line called SCL. Each slave device on the bus has a unique address, so the master can talk to specific devices individually. This is incredibly useful for connecting many components without using up lots of your precious GPIO pins.
Multi-drop on just two wires. Very efficient.
Extremely. And another major one is SPI, the Serial Peripheral Interface. SPI is generally faster than I or C. It typically uses four wires, one for the clock, SCLK, one for master out slave in data, OMIOSI, one for master and slave out data, MISO, and one for selecting which slave device the master is talking to, slave select or chip select, SSES. A key feature of SPI is that it's often full duplex, meaning data can be sent and received at the same time because of the separate MOSI and MISO lines. It's commonly used when you need higher speed data transfer, like interfacing with SD card modules, faster graphical displays, or some types of sensors that produce a lot of data quickly.
Faster, four wires, good for high throughput.
Exactly. So UART, I2C, SPI, these are fundamental hardware-level protocols. Choosing the right one for your needs and wiring it up correctly is a core part of designing and building any non-trivial IoT device.
It really shows how much goes into making these components talk to each other reliably.
It does. It's the hidden language of hardware.
We've covered an incredible amount of ground today, from the tiny sensors detecting light and temperature, through the actuators making things move or switch, the microcontrollers providing the brains, and how they all signal and communicate. It really builds a picture.
Hopefully, yes.
So to wrap it all up, our final question, number 14. To conclude our discussion on hardware, what is the key takeaway about the importance of these physical components to the Internet of Things?
I think the most crucial takeaway is this. IoT hardware isn't just part of the system. It's the physical embodiment of digital intelligence interacting with our world. It's the tangible machinery that allows all the clever software, the cloud platforms, the data analytics, to actually perceive what's happening physically and then influence or change it. Without sensors, the system is blind and deaf. Without actuators, it's paralyzed. Without microcontrollers or SBCs, there's no local intelligence to process information and react quickly. They are truly indispensable.
The bridge between bits and atoms.
Perfectly put. Sensors are the senses, actuators the muscles, microcontrollers the distributed brains. And understanding how they handle analog and digital signals using ADCs and DACs, how they connect via GPIO, and how they communicate using protocols like I1EC and SPI, that understanding is the absolute essence of IoT hardware design and implementation. The transformative power of IoT that we hear so much about is directly tied to the relentless progress being made in these hardware components, making them smaller, cheaper, more powerful, and more energy efficient every year. That's what lets us embed this capability into practically anything.
It makes you think about the future, too.
Absolutely.
Yeah.
While there are still significant challenges, things like power management, keeping billions of devices running, ensuring physical security, and dealing with electronic waste, the trajectory is clear. We're seeing advancements in nanotechnology and material science that promise even more incredible hardware. Maybe self-powered sensors, biocompatible ones we can use medically, sensors so tiny they can be woven into fabrics or building materials almost invisibly. We're truly building towards that digital nervous system for our planet.
A powerful vision indeed, and a great summary of why understanding this hardware layer is so fundamental.
It really is the foundation upon which everything else is built.
Well, this has been incredibly insightful. We've gone deep into the physical heart of IoT.
It was a pleasure discussing it.
And it sets the stage perfectly for our next discussion, doesn't it? We've got these devices sensing and acting, but how do they talk beyond the circuit board? How do they connect to each other, to gateways, and ultimately to the internet?
Exactly. As we move from the physical components themselves, our next deep dives will explore precisely that, how these devices communicate over networks. We'll get into the protocols that enable the internet part of the Internet of Things.
Fantastic. So for everyone listening, be sure to tune in for our upcoming deep dive, which will be on communication protocols for Internet of Things.
We'll cover things like Wi-Fi, Bluetooth, LoRaWAN, MQTT, and more. It's going to be another crucial layer to understand. So thank you everyone for joining us on this deep dive into IoT hardware. I hope you found it valuable. For more insights into the cutting edge of technology and to continue expanding your knowledge, please be sure to subscribe to our channel, Tech AI and Beyond.
Thanks again for leading this Q&A. That was excellent. And thank you all for listening to the deep dive. We'll talk to you next time.